Welcome to IT.Solution, your total network, system, firewall, and security partner.
Welcome to this explainer. Today, we are jumping straight into the fascinating journey of a newly booted device on an IPv6 network. Have you ever wondered exactly how a host wakes up and asks the network, "Hey, where am I, and what is my IP address?" Well, we're going to figure that out. IPv6 handles dynamic addressing in a completely revolutionary way compared to the old IPv4 days. We'll be breaking down the core concepts of SRWE Module 8, specifically SRWE CCNA and DHCPv6, so you can see exactly how global Unicast addresses actually get assigned.
Here is our quick roadmap for today. 1. Unlocking IPv6 dynamic addressing. 2. SLAAC, do-it-yourself. 3. Stateless DHCPv6, team effort. 4. Stateful DHCPv6, full control. 5. Decoding router advertisement flags. And 6. Verifying your IPv6 network. We're just going to build up the complexity step by step so you can absolutely nail these CCNA concepts.
All right, Section 1, Unlocking IPv6 Dynamic Addressing. Let's get into it.
So let's set the stage here. When an IPv6 device wakes up on a network, how does it actually know its own address if there isn't a server there to tell it? In the legacy IPv4 world, we absolutely relied on a DHCP server. If a device booted up and that server was down, boom, you were stranded. No network for you. But IPv6, it introduces these brilliant new methods for devices to just figure things out autonomously. By default, an IPv6-enabled router periodically sends out ICMP v6 router advertisement messages, we call them RAs, and these RAs completely revolutionize how a host dynamically gets its IPv6 configuration.
Think of this dynamic assignment process as a sort of branching roadmap with three main paths for getting a global unicast address, or GUA. Over on the purely stateless side, we've got SLAAC only, where the device relies 100% on the router's advertisement. Right in the middle is a hybrid approach, SLAAC paired with a stateless DHCPv6 server. And then, over on the stateful side, we have Stateful DHCPv6, which feels a whole lot more like the traditional IPv4 DHCP you're probably used to. The crucial thing to remember here, in all three scenarios, that router's RA message is the starting pistol. It dictates exactly which path the host is going to take.
Moving on to Section 2, SLAAC, do-it-yourself. Let's explore that first, simplest path. With SLAAC, which stands for Stateless Address Autoconfiguration, the device essentially takes matters into its own hands using a simple three-step checklist. It just chats at the local router to get the baseline details without any central server tracking the IP assignments. That lack of tracking is literally why we call it stateless. Step 1. The newly booted host sends out a router solicitation, or RS message, to the all routers multicast address FF02:2. It's basically shouting, "Hey, I need an RA." Step 2. The router replies with that router advertisement sent to the all nodes multicast address FF02:1. And finally, Step 3, the host takes the info from that RA and builds its very own address.
Now think of building that 12-bit address like snapping together a two-piece puzzle. The router provides the first half, which is the 64-bit network prefix and prefix length. But the host still needs the second half, right? So it generates its own 64-bit interface ID to finish the puzzle and create a completely unique 128-bit address. It's honestly a perfect partnership. The router tells the host what neighborhood it's in, and the host decides its own house number. So how exactly does the host come up with that 64-bit interface ID? It generally has two choices. First, it can mathematically embed its own 48-bit MAC address using a method called EUI64. This basically takes the MAC address, slices it right in half, shoves the hex value FFFE right in the middle, and flips the 7th bit. It's a clever way to guarantee uniqueness, but it does expose your actual hardware MAC address to the outside world, which is a pretty big privacy concern. Because of that, the second option is much more popular today. Just generate a random 64-bit number. In fact, modern Windows hosts default to this randomized method specifically for privacy.
Okay, but wait, if all these hosts are just randomly generating their own IP addresses, how do we make sure two devices don't accidentally pick the exact same one? Well, before officially claiming this self-made address, the host runs a quick Duplicate Address Detection Check, or DAD. It sends out an ICMP v6 neighbor solicitation message containing the last 24 bits of its shiny new address. If the network is quiet and no other device responds with a neighbor advertisement, the address is virtually guaranteed to be unique, and the host confidently locks it in. Section 3. Stateless DHCPv6. Team effort. Now what if our self-configuring host also needs some extra info, like the address of a DNS server or a domain name? SLAAC alone cannot do that. This is where the router steps in as a traffic cop. Using the command IPv6 end other config flag on the router, it changes its RA message to essentially tell the host, look, go ahead and build your own IP address and default gateway using SLAAC. But for everything else, like your DNS server, go ask that DHCPv6 server. We still call this DHCPv6 server stateless because it's not tracking IP leases, it's literally just handing out a generic copy of DNS settings to whoever asks. Total team effort.
Section 4. Stateful DHCPv6. Full control.
All right, but what if you're a network engineer who demands absolute iron-fisted control over every single IP address assigned on your network? For that, you're going to use Stateful DHCPv6. On your router, you'd apply the IPv6 ND managed config flag command. Once you do that, the router's RA message changes its tune. It tells the host, do not use SLAAC for your IP address. Go talk to the DHCPv6 server for absolutely everything. And the server here is stateful, meaning it meticulously logs and tracks every single client lease, matching MAC addresses to IPv6 addresses. The only thing the host gets from the router in this scenario is its default gateway, which is just the router's link local address.
Section 5. Decoding router advertisement flags.
So how does the router actually control which of those three methods the host uses? It's all about setting specific flags in the RA message. Think of this breakdown as your ultimate CCNA cheat sheet. The A, O, and M flags are the precise signals dictating the host's behavior. The A flag stands for Address Auto-Configuration. If that is a 1, the host uses SLAAC. The O flag is for Other Configuration. A 1 here means the host needs to seek out a stateless DHCPv6 server for things like DNS. And the M flag stands for Managed Address Configuration. If that is flipped to a 1, the host has to use a stateful DHCPv6 server for its actual address. So for SLAAC only, just the A flag is 1. For stateless DHCPv6, both A and O are 1. And for stateful DHCPv6, only the M flag is 1. Pretty straightforward once you see it laid out.
Section 6. Verifying your IPv6 network. Let's wrap this up with some practical application.
To really bridge the gap between theory and practice, you have to understand the actual message flows and the timeline of these operations. The difference in communication overhead is honestly stark. With SLAAC, it's this beautifully simple two-way exchange. The host sends a router solicitation, the router fires back a router advertisement. Bam, done. But DHCPv6, that is a much heavier four-way process. The client sends a solicit message to all DHCPv6 servers on UDP port 547. The server replies with an advertise. The client follows up with a request, and finally the server sends a reply. If you're studying for your CCNA, that probably sounds awfully familiar, right? Because it's basically the exact same concept as the IPv4 DHCP DORA process.
Of course, when you're actually on the job verifying or troubleshooting this stuff, you need your command line tools. On the router, running show IPv6 interface is your best friend for checking which ND flags, like managed or other config, are actively set. If you're running a stateful server, running show IPv6 DHCP pool and show IPv6 DHCP binding will prove beyond a shadow of a doubt that addresses are being actively leased out. And for the client side, if you're on a Windows machine, just run good old ipconfig/all. That will instantly tell you whether your device generated its own SLAAC address or pulled one from a server, plus it'll show you your dynamically learned default gateway.
So, here's a thought to leave you with. In a world of literal billions of IoT and mobile devices, will you let them effortlessly configure themselves using SLAAC, or will your environment require the absolute tracked control of stateful DHCPv6? As you design your networks and as you tackle these SRWE Module 8 concepts, that choice is entirely in your hands. SLAAC scales like an absolute dream, but stateful DHCP gives you that legacy enterprise auditing power. Which one does your network truly need? Thanks for hanging out with me for this explainer. You are now officially empowered to go out and master IPv6 dynamic addressing.
Thank you for watching. See you in the next episode.